You know, when you hear that some AI model has learned to spot cats in photos or even write poetry, what does that actually mean? How does a machine with like a billion different settings go from knowing absolutely nothing to doing these incredible things? Okay, let's get into it. We're going to go on a journey to find out how an AI finds the one perfect answer in a whole universe of wrong ones. So here's the plan. First, we'll get a handle on just how massive this problem is. Then we'll grab our most basic tool, something called gradient descent. We're going to see where it breaks down, and then we'll upgrade it with some really cool tricks like momentum. And finally, we'll meet the hero of our story, Adam, the all-in-one solution that everybody uses. Let's get started. All right, first things first, we need to appreciate just how mind-boggling the challenge is. These modern AI models, these neural networks, they can have billions of parameters. So picture trying to perfectly tune a billion different knobs, all at the same time, to get one perfect outcome. It's a task that's just completely impossible for a person to do by hand. So this whole process of training an AI is really just about finding the perfect setting for all of these little knobs, which are technically called weights and biases. The whole goal is to tweak and adjust every single one of them until the model makes as few mistakes as it possibly can. In other words, we want to minimize its loss. The real question is, how on earth do you automate a tuning process that massive? Okay, so our very first tool for this job is this incredibly powerful but really fundamental algorithm called gradient descent. It is the absolute cornerstone of how pretty much all neural networks are trained, and honestly, it's based on a surprisingly simple idea. To really get gradient descent, we're going to use a metaphor that's going to stick with us. Imagine that every possible combination of those billions of knobs creates a vast 3D landscape, a huge foggy mountain range. The height at any point on this landscape tells you how wrong the model is. That's the loss. Our goal? It's simple. Find the lowest possible point, the absolute bottom of the deepest valley in the entire range. And we are a hiker, lost somewhere in this fog, trying to find our way down. So how does our hiker do it? Well, it's a simple three-step dance. First, our hiker feels the ground right under their feet to figure out which direction is the steepest way down. In math speak, that's called calculating the negative gradient. Second, they take one small step in that direction. And third, they just do it again and again and again. Feel the slope, take a step. Feel the slope, take a step, all the way until they can't go any lower. So this brings up a huge question. How big should those steps be? This is an absolutely critical setting called the learning rate. You'll often see it represented by the Greek letter alpha. The math you see here basically says our new position is just our old position minus a little nudge in the right direction. And that alpha right there, the learning rate, controls just how big that nudge is. That one single number has a massive impact on our hiker's entire journey. But, as elegant as this sounds, it's not quite that simple. Our hiker can run into some really big problems out there in the fog. The path down the mountain isn't always smooth, which brings us to the flaws in this basic approach. This is the great learning rate dilemma. If our hiker's steps, the learning rate, are way too small, sure, they'll get to the bottom, eventually, but it could take forever. On the other hand, if their steps are too big, they might literally jump right over the lowest point of the valley and start bouncing from one side to the other, never actually settling down. Or even worse, they could launch themselves to an even higher point on the mountain. And that leads to an even sneakier problem. Remember, our hiker is in a really thick fog. They can only see the ground, like right at their feet. So when they finally reach the bottom of a little dip and can't go any lower, how do they know it's the actual lowest point in the whole mountain range and not just some tiny pothole on the side of a much, much bigger mountain? This is the classic trap of a local versus a global optimum. A local optimum is a valley that feels like the bottom from where you're standing, but the true global optimum, the real prize, might be miles away. And for these super complex neural networks, the landscape is absolutely littered with these deceptive little traps, and our simple hiker gets stuck in them all the time. Okay, so our basic hiker is a little naive. They get stuck really easily, and they're super sensitive about how big their steps are. To fix this, we need to give them some upgrades, some high-tech hiking gear, if you will. The first upgrade is called momentum. And the best way to think about this is we're not just a hiker anymore. No, we're a giant boulder rolling down the mountain. As that boulder starts to roll, it builds up speed, it builds up velocity. And that momentum helps it just crash right over those little bumps, our pesky local minima, and it naturally goes faster and faster on those long, straight downhill parts, which really speeds up the whole journey.
So how does this work under the hood? Well, the key here is that v term. That's our velocity. To figure out our new velocity, we take a fraction of our last step's velocity, that's the beta times v part, and we add it to the push from our current step. That beta acts like a memory. It reminds the boulder which way it was already going, so it tends to keep going in that same direction.
All right, our next upgrade is called RMS Prop. This is like giving our hiker a pair of intelligent, all-terrain hiking poles that can change their length on the fly. In places where the terrain is really steep and rocky and bouncy, places where our hiker might overshoot, the poles automatically shorten to take smaller, more careful steps. But on the flat, boring parts where progress is slow, the poles get longer to take these huge strides and cover more ground.
So how does it pull this off? Well, the update rule basically divides the learning rate by a running average of how steep the slope has been recently. So if the slope has been really steep and bouncy, that number on the bottom gets bigger, which makes the step size smaller. If the slope has been gentle and consistent, that bottom number gets smaller, making the step size bigger. It's totally adaptive.
So we've got momentum, which gives our hiker mass, and we have RMS Prop, which gives them adaptive footing. What if we just combine them? Well, that brings us to Atom. Atom is basically our pro hiker, equipped with all the best gear money can buy. Atom, which stands for Adaptive Moment Estimation, does exactly that. It literally takes the velocity building idea from momentum and smashes it together with the adaptive learning rates from RMS Prop. It even adds a clever little correction to make sure it works great right from the very first step. And because of all this, Atom is pretty much the default go-to optimizer for almost every deep learning problem out there today. Now, I know this formula looks a little crazy at first glance, but it's really just elegantly combining the two ideas we just talked about. This first part, which tracks the mean of the gradients, that's the memory from momentum. And the second part, which tracks the variance, that's what gives us the adaptive steps from RMS Prop. Atom just puts it all together into one super powerful package. So what does all of this actually mean in practice? Well, it means a much faster and more reliable trip to the bottom of that valley. If you imagine a race between these different hikers, our basic one, using what's called stochastic gradient descent, or SGD, just plods along slowly. Adding momentum or RMS Prop gives it a huge boost. But Atom consistently wins the race, finding a great solution way faster and with a lot less fuss. So we've equipped our hiker with some amazing, powerful tools. But the truth is, the journey of optimization, of finding that perfect lowest valley, it's never really over. The last big question is, which one of these tools should you pick for your journey? And honestly, the takeaway here is pretty straightforward. Atom is your standard default choice. You start with Atom. It just works well out of the box for most problems. Now, SGD with momentum is a really strong alternative. Some research even shows it can sometimes find better valleys, but it usually needs a lot more careful tuning. And then you have other methods like LBFGs, which are super powerful, but they don't really work with the way modern deep learning is done. So there you have it. We've gone from a simple hiker feeling for the slope in the fog, all the way to a pro explorer with adaptive gear and unstoppable momentum, all just to find that lowest valley. But these AI landscapes, they're getting deeper and bigger and way more complex every single day. And it just leaves you wondering, what new tools, what new strategies will the next generation of AI explorers need to navigate the real frontiers of intelligence?